Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on January 29th, 2026, just 2 days ago. It introduces a lightweight 4 billion parameter model that unifies text and vision-centric OCR, effectively outperforming massive models like Gemini 2.5 Pro on the OmniDoc benchmark with a score of about 89.2. The paper is titled OCRVerse, towards holistic OCR in end-to-end vision language models. And as we'll see later, the results for complex tasks like rendering scientific plots from images are really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 breaks down these capabilities, comparing OCRVerse against both specialized and general-purpose models. The top row focuses on text-centric tasks like reading tables or formulas, where the model, shown in the blue bars, remains highly competitive despite its smaller size. But the bottom row highlights its true strength in vision-centric challenges. For example, in the Image-to LaTeX plot benchmark, which tests converting plot images into code, OCRVerse actually surpasses GPT-5, scoring over 63 compared to GPT-5's 57. To support these broad capabilities, Figure 2 illustrates the comprehensive data coverage used for training. The left panel displays the text-centric scenarios, covering 9 traditional document types like magazines, exam papers, and reports, where the primary goal is accurate text extraction. In contrast, the right panel highlights vision-centric data, such as charts, web pages, and circuit diagrams. For these inputs, the model must generate structured, code-level outputs to fully capture the visual relationships. Alright, ensuring high quality across all those diverse sources requires a robust process, which Figure 3 details here. The top pipeline handles text-centric data, where raw inputs like PDFs or synthetic text go through rigorous cleaning to remove issues like reversed ordering or duplicated blocks. Then, the team uses strong existing models, specifically Qwen 2.5VL and GOT, to generate accurate ground truth annotations. Meanwhile, the bottom pipeline processes vision-centric data like charts and web pages. Here, the focus is on self-annotation, where the system verifies data by rendering the code, such as HTML or SVG, back into images to ensure the structural layout matches perfectly. So after preparing the data, Figure 4 maps out the complete 2-stage training strategy. The left panel shows Stage 1, supervised fine-tuning. Here, the model establishes a unified representation space by training on the mixed cross-domain dataset we just discussed. Then, the right panel details Stage 2, which uses reinforcement learning to optimize specific skills. The top section illustrates how they build the training data by filtering out low-quality samples. Crucially, the bottom loop introduces personalized rewards. For text, it uses strict rules like string matching, while for vision tasks, it renders the output code and compares it visually to the original image using a Dino v2 encoder. With the training process complete, Table 1 reveals the results on the OmniDoc Bench v1.5 benchmark. The General Vision Language Models section in the middle lists major competitors like Gemini 2.5 Pro and Qwen 2.5VL. Surprisingly, the OCRVerse model, located in the very last row, outperforms these general giants with an overall score of 89.23. It also remains competitive within the specialized vision language models section, surpassing strong systems like DeepSeek OCR. Okay, moving to Table 2, we see the performance on vision-centric tasks, specifically those requiring code generation like charts, S versus Gs, and chemical diagrams. The table compares OCRVerse against top-tier closed-source models in the upper section and various open-source baselines in the middle. Looking at the bottom row, the results are remarkable for such a lightweight model. For instance, in the Uni SVG column, OCRVerse achieves a score of 76.3, which actually outperforms Claude 4.5 Sonnet and nearly matches GPT-5. Even more striking is the Image-to LaTeX plot benchmark toward the right, where it hits an 88.7% rendering success rate, beating every other model on the list. Wrapping up, 2 things stand out. First, this model successfully bridges the gap between traditional text reading and complex visual understanding. Second, it proves that a compact 4 billion parameter architecture using smart reinforcement learning can rival or even beat massive proprietary systems. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.